we are going into the concept of passive networks. Yeah. Now, transmission lines is one thing, but just having a transmission line is no use, right? You have a subsystem here and you have a subsystem here. You want to connect this system to this system, right? So how do you characterize this system? So this can be made up of certain components, what are called as RF components. Specifically, we're going to be looking at passive components. To understand passive components, we get introduced to what is called as network theory, a theory just like transmission theory, where you will end up describing, not understanding what's going on inside the network, but in terms of what happens at the terminals. Just describe it in terms of what happens at the terminal. That's good enough. You don't want to know what is happening inside the network. So that point where energy goes in or out of the network is called as a port. It's called as a RF port or port. Just like how in a country, port is where goods come in and go. Yeah. Similarly, for this system, the RF energy that comes in and goes called as the port of the system. And it needs to have two conductors to make one port, which carries the V plus and the V minus, or the I plus and the I minus, or power in and power out. Equivalently, all of them are the same. So you can classify as one port networks. The two conductors are this. You have a plus and minus. This can carry the plus current and this can carry the minus current. You can have two port networks where this is port 1 and this is port 2. So in general, you can extend the concept to n ports. Yeah, 1, 2, 3, so on up to n ports is possible. The system can have as many ports. So if you look at a typical communication system, an amplifier would be a 2-port. A filter would be a 2-port, one in and one output port maybe, yeah, because it's directional. An antenna is going to be simply a single port. That means RF energy can either flow in this way or this way, but there is only one point where it gets connected to the system. Now, without knowing what is inside the system, how would you want to characterize the system? That means, given a certain input, you want to know what is the output, but you don't want to know what is inside. Because let's say there is Huawei is doing this RF board. Yeah, they wouldn't want to disclose what is going on inside, right? All they will say is, hey, if you give this input, I can tell you what your output is, but I will not tell you what's going on inside. But then you as a customer will say that, hey, I want this kind of output for a certain input. Your system should be able to provide that. So your system is a black box to me, but all I need is this output for a given input. How to describe the network in terms of a certain parameters that allows you to do that. You don't go into the internal details of the system, but you just know what is the output given an input. The best parameter that is what is called as the Z parameters, or the impedance matrix Z parameters, which relates the port voltages to the port current, port voltage to port current. Similarly, Ohm's law, V equal to IR is the same thing. Yeah, instead of R, you're having a complex impedance. So if you have a 2-port system, this becomes a matrix. That means the voltage at port 1 is not only depend on the current at port 1, but can also depend on the current at port 2. Similarly, your voltage at port 2 does not only depend on the current at port 2, but also can depend on the current at port 1. It can be a complex network. You don't have to worry about it, but there is whatever current here can influence both V2 and V1. This current can influence both V1 and V2. So how do you obtain these guys? If I take this equation only, it's going to be Z11 I1 plus Z12 I2. And I notice that if I want to find what is Z12, so if I want to find what is Z12, I can always say, if my I1 is 0, if under the condition that I1 is 0, I will see that this term goes to 0. I can say my Z12 is the same as V1 over I2 when I1 is equal to 0. That's what we describe here. But I1 equal to 0 means what? There will be no current flowing here if this is left as an open circuit like this. If it's left as an open circuit, when it's not connected to any load, when it is left as an open circuit. So By now you will see that short circuit, open circuit, and match. These three are important loads. So open circuit, I1 is 0, so you can simply find what is Z12. Similarly, you can extend the concept to find the Zmn for an n by n, for a n by n. This must be capital N for an n by n matrix. For passive circuits, this matrix is symmetric matrix. That means this term is the same as this term. This term will be the same as this term. This term would be the same as this guy, so on and so forth. That is true for a passive circuit. That means how I1 influences V2 is the same as how I2 influences V1. Yeah, because it's a symmetric matrix. Similarly, you can define what is called as a white matrix, but all I need to know is what are the port currents, how are they related to the port voltages. Again, you had V equal to IR before, you can also have I equal to V over R. The Ohm's law, the same Ohm's law. So instead of 1 over R, you're having it as Y. So again, for a 2 by 2, it's going to be a matrix. And this matrix, you can find out Y12 when V1 is equal to 0. That means the voltage at port 1 is 0. When will the voltage at port 1 be 0? When I make it a short circuit. If I connect it as a short circuit, then V1 is equal to 0. So unlike the Z matrix where you had an open circuit, for V1 you're having a short circuit. So you used open circuit for Z parameters, short circuit for Y parameters. You can extend it similarly.